Good morning, all. Today we would start the demonstrations of virtual lab experiments. I would, along with two of my colleagues, would try to give you a flavor of what these V labs are about. Of course, there has been a lot of introduction, and Professor Srinivas Rao Garu, Professor Charan Garu, all these people have already explained why we are in requirement of this virtual lab scenario. Okay, so what are the different types of virtual labs? This is what I thought I should start our discussion with. We can have a modeling, simulation-based lab. You can have measurement-based lab. You can have remote trigger lab. Now, the point about this remote triggered measurement-based are like you have your instrument somewhere in remote areas and you can sit at home and you can operate it. The other one is the modeling simulation-based, which have two purposes. One is like you can do the simulations on some clusters. This happens for all the theoretical or computational experimentalists or computational researchers. The other one is what actually we are trying to do. We are trying to simulate what is happening in the lab atmosphere. Okay, so why is it gaining more preference? It's not just the COVID issue. It is also found that a gamified laboratory simulation motivates students and improve learning outcomes compared with traditional teaching methods. Okay, now, of course, given the present scenario, we think because of COVID, the virtual labs have become more important, but this is not the case. Virtual labs have been introduced by MHRD and also by the Indian government, as well as a lot of other governments all across the world, because it has got its own benefits. As the Honorable Vice Chancellor of JNTU has mentioned, a blend of virtual as well as the real teaching methods would have a more effect on the students. And now with the present generation of students who are more attached to their mobiles or gadgets, something to do with online way of teaching is now very important. Okay, so what are the things which help us? One is you can have online labs, you learn at your own pace. Integrated learning, most of the times you will have contents in one place. The self-evaluation, you can have pre-post lab quiz. This is though for those who are true to themselves, honest. There is a better insight in terms of animations, video threat. It depends on how which person is doing this, giving you the VLABs. But an animation is always a picture says better than 1,000 words, and that's what it is. If we see it, we can understand much better. Another point which was highlighted by one of the previous speakers is you do have freedom to make mistakes. You can make experiment with experiments. You have no problem of burning things. You don't have anything. So it is, I would say, take virtual labs with a pinch of salt. Yeah, you can do many things. There are a lot of good things. At the same time, for sure, whenever there is an opportunity to come back to the lab and start working, there's nothing like touching the instruments and learning. And that's the true learning. Okay, that's something which we need to keep in mind. Then comes this initiative by MHRD. Okay, so this because this I'm giving the first talk on VLabs in this FDP. I thought I should briefly mention what our VLab, our MHRD is doing, Ministry of Human Resource Development. Now I think the name has changed. Okay, so this is the URL. Okay, the objectives is what you mentioned here. You can see it in the website to provide remote access to labs in various disciplines of science and engineering, to enthuse students to conduct experiments arousing their curiosity, to provide a complete learning management systems around the virtual labs. Now you can read it, and to share costly equipments and resources. So all these things are there, and importantly, from my point of view, I find the salient features more important, more interesting. So virtual labs will provide the student the result of an experiment by one of the following methods: modeling the physical phenomena by set of equations and carrying out simulations to yield the results of a particular experiment. Earlier, we used to have personal interest. Students were those who want to just model. They can take a theory from the textbook, an equation from the textbook, use C programming or MATLAB programming, and try to simulate it and look at it. But then that kind of learning, no doubt, is very interesting, and one can do many other things with if you can do it yourself. The number of students who are able to do that were limited. With the access to these virtual labs, All those things are now free of cost to anyone who wants to try out things. So as soon as a theory class is done, one can quickly augment it with a virtual lab demonstration so that animation as well as putting in the actual numbers give you as an information. So this way, all the colleges who are remote, who do not have access to the equipment or who do not have access to the labs, are able to gain much more exposure. And another point is one can also provide visual data to virtual experiments. It is a possibility which one is also doing, remotely triggering an experiment in actual lab setups. And importantly, virtual labs will be made more effective and realistic by providing additional inputs to the students, like accompanying audio and video streaming. So most of the features are already incorporated in the website. If you look at it, you have various buttons. And in fact, the participating university institutes are this at the moment, where each of them have given their own experiments. It's all available. And more colleges are now getting in trying to do it. And with this current situation where COVID is forcing everyone to come up with innovative solutions, I am sure by end of this year, there may be lot many more resources which is floating outside. So having said this much, I would stop it and we go to the our demonstrations which we planned for today. My theme of the next 1 hour, 1.5 hours is to demonstrate 3 experiments in the modern physics theme. So I picked up determination of Planck's constant, photoelectric effect, emission spectra as 3 representative experiments. Okay, so what I would do is the following. I would explain each of the experiment. I will go to the website, show or demonstrate how one can do that actually on the website. Okay, and then get some numbers and see how to find the actual solutions for that. Okay, in case anyone has any trouble listening to me, please come up message me so that I can stop or wait for you. So as long as I don't get any information from you, I would assume that you're able to listen and see me and also follow the demonstration. Okay, yeah, right. So this is the first experiment, determination of Planck's constant. So this is taken from the majority of the physical sciences experiments. So you can just go to their website or type Amrita Vidyapeetham, Vishwavidyapeetham, VLabs, do whatever you done and you will get all these things. So this is the URL, vlab.amrita.edu, and you're going to see a lot of other things. Okay, so this is taken under the theme of physical sciences, modern physics virtual lab, demonstration of Planck's constant. So this is how one reaches to this place. And I'm going to show you how it looks. So you have an aim, the theory is there where you talk about aim, apparatus, etc. Then you have a procedure where you can you learn how to use the simulator. So this is the simulator. The only problem which I am forcing with all these virtual labs is the requirement of flash. Google Chrome seems to be stopping the Chrome by end of this year. So something else will come up for sure. But in the meantime, we need to stick to the Flash. Okay, so you need to install Flash on your web browsers, and then you can start looking at the simulator. So this simulator, the way it works is explained in the procedure. You do have the self-evaluation tool where the few of the questions are given so that you can learn or you can answer them to test your understanding. There is certain assignments given where one can play around with whatever is there, and you can do a little bit of notes and other things. You do have reference and feedback. So in case you want to do some more, or you want them to do something more, or there are some technical glitches, you can always get back to them. And personally, I felt this is really well developed virtual labs, and I really appreciate the initiative by Amrita Vishwavidyapeetham. And they did a really good job. I think when you go through the entire website, you will realize why I'm saying it. Okay, let's get back to the determination of Planck's constant. So the point is, I have chosen a very, very simple experiment to begin with. Another point which I should also notice is that the entire VLabs are free to access. Okay, so all the participants, please keep in mind, it is instant. So you can, in principle, access this free of cost. And if you're used to it, one can And another point which I have realized is it doesn't require too much of bandwidth to try out. So you can have good time learning. That's what is my suggestions to you. Okay. So it's a very simple experiment, and this is the beginning of the quantum physics. So to introduce what is Planck's constant, it is a fundamental physical constant and determines quanta or small packets of energy along the frequency of radiation. It describes the behavior of particle and waves at atomic level. So this is how one can teach the idea of Planck's constant to a student. Okay, and here we would do the experiment with LEDs. Now, if someone asks a student, or if you ask, what is the proof of quantum physics, quantum Planck's constant, etc., you can simply show an LED which is used everywhere and say that this is a demonstration or the proof of the success of quantum mechanics. Okay, so it's something which one should keep in mind. And this experiment of determination of Planck's constant is done with the use of LEDs. So I'll just explain you how it is done. So keep in mind, LED in unbiased condition has a potential barrier which is developed across the PN junction. So when we connect the LED to an external voltage in the forward bias direction at a particular voltage, the height of the potential barrier becomes very low and the LED starts glowing. That is, in a forward bias condition, the electrons crossing the junction are excited, and when they return to the normal state, energy is emitted. Right? So these are all things which you all know. I just want to refresh you so that we can understand, we can go with this experiment. So this particular voltage is called the new voltage or the threshold voltage. Once the new voltage is reached, the current may increase, but the voltage doesn't change. The other point is, once the new voltage is reached, you may increase the light glows, right? You have the output of the LED. Okay. Now, some little bit of theory, what we get out of it, once we know the light using forward bias is given by E equal to hc by lambda. Okay. Here I have shown you some colors. So each color will represent a certain wavelength. If V is the forward voltage applied across the LED, when it begins to emit light, that's the new voltage, the energy given to the electrons crosses the junction. So you provide sufficient energy to the electrons to cross the barrier. Okay. And so the energy which comes out should be equal to the E times V, where E is the charge and V is the voltage we are going to apply. It's the forward voltage. Okay, so one can use these equations to get this find EV equal to hc by lambda, and so you can demonstrate or you can determine the Planck's constant by having the knowledge of what is the new voltage for a certain wavelength lambda. Okay, so the idea here is that you take different LEDs, which gives you various wavelengths, and you work out or you do an experiment which tells you what is the new voltage for each LED to glow. So the product of the new voltage and the wavelength multiplied by the ratio of E by C gives you what is the Planck's constant. So the experiment is very simple. I thought we should start with something which is very simple to get it so that we can go with the flow. So this is how it is, EV equal to hc by lambda. Okay, you can also calculate. You can also write the same thing with V equal to hc by E and 1 by lambda. Okay, the reason why we do this is, if you look at it and you carefully understand, so there is a constant C by E, right? There is a certain constant. So V is proportional to h by lambda. Okay, and so if you take a graph of the inverse of wavelength versus the new voltage, it should have a straight line. Okay, and then the slope of it would give you a information about the Planck's constant. So this is an alternative way of determining the Planck's constant. Okay, so you can have graphical way as well as certain direct calculations. So this is the objective, determination of Planck's constant. As I said, the idea is to glow your bulb at Bijli, glow your bulb or glow your LED. Yeah, and so for that you need a potential. So this is the circuit you take. You vary the voltage till you reach a new voltage. Okay, and then at the new voltage, the light glows. And so one needs to have an experiment where all these various things are there, and you need to give the connection and vary the voltage and keep track of what is the output voltage and what is the output voltage. You can keep track by making a circuit where the voltmeter is parallel to the LED, and the current one can see to one can have it in series, so that you also know how much current is flowing in the circuit. So all these things are clear. Okay, so this is how the experiment setup looks like. So all of you who have done experiment in the lab can quickly visualize what each of it is. You have a battery, you have a rheostat, then you have a key or a switch, an ammeter, so a voltmeter, ammeter, a resistor, and then LED. So basically the different parts which are there, and the variables in the experiment is the uh, various LEDs. Okay, so that's what we will do. I'm going to show you slowly what I mean by it. So when I show you the thing on the website, there is certain things to keep in mind. One is you need to place the mouse pointer over the component to click and drag wire. Now there is no physical wire. You can connect them by using your mouse. Okay, and when you put the mouse on that, you will see this nice hand button. Okay, and then that would allow you to connect the way you want. Okay, so another point is choosing the wavelength. So you need to choose the wavelength. So you have red, green, yellow, blue, infrared. Okay, so these are the various things you can see. Of course, infrared, I just put a question mark because we cannot see the light, but then you know the LED is working when, how do you know? When you keep changing the voltage, the output voltage remains the same, whereas the current increases, the circuit increases. So that's when you know that the uh, light is coming out of infrared LED. So all these options are there in the website, okay, in the V Labs, virtual labs, right? And then another point is that unless you do a proper connection, you cannot start the experiment. Okay, so I'll just demonstrate to you also. So you need to, this way what happens in the lab, the reason why we always put a key here is to make sure that all the connections are there, so that you put the key to close the circuit. Otherwise what happens, you have short circuit and things will burn out. So this is the idea of the key in the real lab. The same thing is simulated here, right? The same thing is simulated here. And so this experiment doesn't let you to start unless you have all the collections perfect. Okay, so this is another way of having a simulation close to the reality. That's very nice thing about this virtual lab, right? And then you keep varying this rheostat. Okay, by changing the rheostat, you vary the battery, the current from the battery output. Okay, the bias you change by rheostat, and then at a certain value of the rheostat, you will see the light glowing, which we call as the new voltage. So as you change this guy, this number goes up, this number also goes up, but then at certain point, you have the light coming out at that point, at the particular voltage at which this bulb, the LED glows, you call it as new voltage, correct? And then you can keep monitoring the current also, just to see how it is, and then you make a note of it. So what you have is a volt. So you have the LED wavelength, 650 nanometers. So you know what is lambda. So now you know what is the new voltage, and then you can get a result. Also, you can make your note the way, use your pen and paper. You can start doing it. Okay. In addition, you can also say show results so that one can check what is the output as per the simulation. So, right. So I have done the experiments. What I will do is I will demonstrate whatever it is, and then we see how one can check it out. Okay. Stop the sharing here, and I go to the Chrome. Hold on, please. I do have problem with this. Yeah. Okay. So you see, let me just remove other things which are not needed for us at the moment. Okay, so this is the virtual lab website. You have theory which talks about aim, apparatus, and other things. Then you have the procedure, okay, where whatever I just showed you is here. Okay, I just took out from this so that you have understanding of everything. You do also have self-evaluation where few questions are given, like LED stands for. So these are the questions which are given, and then simulator, which is the actual interest to us. Okay. So as soon as you click the simulator, you need to log in. So I have my own login password. I can just use it. Looks like there are a lot of people trying today. This field labs. It's taking a lot of time to open. If it continues that, then probably I'll not show you after this. I'll just quickly jump to the main thing. Okay. Let's wait for a couple of minutes to open. Just do once more. I'll do the same thing again. Hold on, please. Okay. So it tells you to detect flash player. Okay. I do have my flash player installed here, so you need to check it out. This part. So earlier it was not the problem. Okay. Earlier everything used to be there, but because now Chrome is not allowing you to do this flash experiments, you need to do all this process. But it doesn't take more than few seconds to do it. So this is how it is, right? So I hope you're able to see everything. So what I do is I select a color. So first thing is I need to select a color. I'll do it little later, but let me do the connections as I showed you earlier. So I can collect it this way. Okay, so just keep in mind, I'm just doing the same thing, whatever is there. Okay. Give me a minute. Yeah. So basically I've tried once, so I know how much to do it, but it's easy. Just follow this circuit so you know where to connect what. Okay. So now you insert the key. Once you insert the key, then everything is ready. Then you have the option of putting the color, whatever color you want. So let's start with the red LED which we start. Okay. So what I do is I change the rheostat. Okay, keep noting the output voltage is changing as I change the rheostat, but there is no current in the circuit. Okay, there's no current in the circuit. No current, no current, no current. Exactly at 1.89, you start seeing some current. Okay, I just play it again. No, 1.8, nothing is there. At 1.89, current starts coming. So the knee voltage here is 1.89 and the voltage, the wavelength is 560. So if I come down, I do have option of adding the, so you see this thing, I have plus, so I can create my own table here. Okay, so I say it is red. The wavelength is 650 nanometers. Okay, the knee voltage is 1.89 volts. Okay, so automatically it does the calculation, gives you 6.552 10 power minus 34 as the Planck's constant. Okay, I would just do the same thing for the next color. Let's choose a green color, which is 510 green. Okay, so let me add another column, another row, green 510. Okay, now I need to check the what is the value of the rheostat I need to use. Okay, so you see that already there is a color by there is a light already available. Okay, so I need to slowly change. Yeah, at 2.4 it glows, correct? 2.4 it glows. So 2.4 is the knee voltage for this. So I put 2.4. Again, you do have it. So that way you may actually change all the colors and get your own table, and you can fill this H, and then you may check out what is the mean value of Planck's constant you get for various LEDs. Okay, so this is how one can do the experiment, right? So I shop it and I move to my PPT. Okay, so this is what I did. So I have completed my observations, right? So I have completed my observations and I found that the H changes 6.55, 6.8. For green, it comes to 6.52. For yellow, it comes to 6.50 blue, and so on, and get the average H to be 6.53, 10 power minus 34. Okay, this is the values I got. Also, as I mentioned to you, you cannot see LED, but then you may keep playing with it to make sure that the current is not equal to zero. The voltage at which the current changes, you know this is the new voltage, and it turns out to be 1.11 volt for the LED. Now, the second experiment what you can think of is, now the point here is that we are given an LED, which is IR diode, and we are not knowing what is the wavelength. So from this earlier experiment, you know what is the H you get, and so you can use the Planck's constant in this equation to get the actual lambda, right? So you can use the, so this is how you can do two experiments. So this is the standard things which we ask the students to do in the lab also. Further continuing, okay, as I mentioned to you, one can plot voltage versus inverse of lambda, inverse of wavelength graph. Okay, so this is the different new voltages for different wavelengths, and I have just plotted with respect to the inverse of the wavelength. And so it fits. You can use a linear fit to get that slope, and from the slope you can also calculate what is the value of the Planck's constant. So this is how one can do the Planck's constant experiment, and so you can go back and do everything whatever it is. So because this is the first experiment which is which is what I'm demonstrating. I have completed all the formalities, whatever is there in the experiment. Okay. For next two experiments, what I will do is I will not fill the tables. I'll just do one or two and show you so that you can go back and start doing it yourself and learn how to use the and familiarize yourself using the virtual labs. Okay. So I hope I'm clear till now. In this experiment, I just introduced you whatever one can expect from the online portal. One can online portal, and I also showed you how the online portal can be used and demonstrated how to get the numbers out of it. So for all those faculty who is listening to me, and for all those who know how we do in the experiment, whatever we do normally in the lab is more or less very close to what is being simulated here. The only thing which we miss is the experience of handling the instruments. But given the present COVID scenario, where learning itself is difficult, I think some learning is better than no learning. So this is where the utility of this virtual labs come from. Okay, so let's move forward and see the next experiment which we planned, which is photoelectric effect. Yeah. So again, this is taken from Amrita Vishwavidyapeetham server. Okay, this is the same thing. So all these three experiments I'm demonstrating is from modern virtual physical lab page. Okay, so photoelectric effect is the next thing. So we have learned about Planck's constant, then we go about photoelectric. So the aim of this experiment is multifold. As I said, there are a lot of things that can do with this experiment. So this is to understand the phenomenon of photoelectric effect as a whole, to draw kinetic energy of photoelectrons as a function of frequency of incident radiation, to determine the Planck's constant from kinetic energy for versus frequency graph, to plot a graph connecting to determine the stopping potential from the photocurrent versus applied potential graph, and finally to determine the work function of the metal. So you can do the experiment, take set of readings, and from each reading you can actually get all these various points which I demonstrated. So here, as I mentioned earlier, I would not do the entire experiment. I would just do this particular thing, which is to determine the work function of a metal. Okay. However, as I would show you in few minutes, the data taken will be the same. The rest is how you crunch the data. Okay, that's where the data analysis is important. Okay, so I would leave majority of this experiment as a assignment for you, so that today evening you can try out. Right? What is the basic theory? This is what is photoelectric effect. We know light incidents on a plate, metal plate, and then if the light is more than hold on please. If it is more than the required threshold, then you have the photoelectrons coming out. Okay, so this is the photoelectric equation, H nu equal to Ke max plus W. Okay, where Ke max is the kinetic energy of the ejected electrons, W is the work function of the metal. Right. So the idea is, if you have a photon whose energy is higher than that of the work function, then photoelectrons are ejected at a certain kinetic energy. Okay, this is something which we all know in the lab. Okay, and the threshold energy is your H nu not equal to W, which is the work function. So therefore, it is important that your frequency is always greater than that of the threshold frequency in order to start seeing the photoelectric effect. Okay. Important points to remember is the number of photoelectrons emitted is proportional to the intensity of the incident light. Also, the energy of emitted photoelectrons is independent to the intensity of the incident light. The energy of the emitted photoelectrons is directly proportional to the frequency of incident light. So these two are the main, the key points to keep in mind when we learn when we teach photoelectric effect to the students. Right. Further going on, we can also make few statements about what is the kinetic energy of the photoelectrons. Okay, given an incident, it's not Hc, it's h nu. I'm sorry. Given an incident photon, we know the energy. Okay, and so if we know the energy, and then we can work out what is the work function, the difference is your h times nu minus nu naught is your Ke max. So this says that the graph connecting the maximum kinetic energy of photoelectrons, Ke max, and the frequency of incident radiation will be a straight line. Okay, this is what it is. Nu minus nu naught, h is a constant. Okay, and the slope with y interstate would be h nu naught or the work. Right? This is how it is. So if you look at this figure, this is something which you also teach in the class, right, to the students. So if you plot, you take a metal, and for each metal, like I explained you calcium, cesium, for each metal I have a mu naught, which is the threshold frequency. And if I keep varying the frequency of the incident light, higher energy, higher frequency, okay, and I plot the nu versus Ke max, okay. Of course, we understand that the kinetic energy keeps on growing as the frequency of the incident light goes higher than the nu naught, okay. And so this would be a straight line, and the slope would give you the information about the Planck space. So this is another experiment one can plan to do it. So what is the experimental schematic from the website, from the portal? So this is how it looks. So you have a light hitting an anode material, which you call as the target. Okay, I just name it as P and Q so that it is clear to us. Okay, once the frequency is greater than the work function of the metal, okay, or the anode metal, photoelectrons start heating, and with higher the nu naught, higher would be the Ke max. So there's electron flow happening this way, the cathode. You can have a connection with rheostat, voltmeter, and emitter. Okay, so you can look at the current in the circuit as well as the voltage in the circuit, right? So as seen from the figure, the light source illuminates a metal plate P, and another plate Q. Electrode collects and emitted electrons. We vary the potential P and Q. So we vary the potential between P and Q, and measure the current flowing in the external current between the 2 points. External circuit between the 2 points. So vary this guy, you change the rheostat, so you vary the bias you give between these two plates. So depending on the bias, the current changes, and if we apply a negative potential to the collector plate Q with respect to P and gradually increase, the photoelectric current decreases. So becomes zero at a certain negative potential. Okay. What do we call this? This negative potential on the collector at which the photoelectric current becomes zero is called the stopping potential or the cutoff potential. So this is again what we also understand from our knowledge of photoelectric effect. Okay. Yeah. So this is the experimental simulator. As you see here, you do have an ammeter and a voltmeter to check it out. Okay. Then you have the source, light source, and this entire connection is within these two, the plates, etc. So we don't get to see the plates and other things. Whatever is to be understood, I just explained in the previous slide, right? So all you do in the experiment is you shine the light, you vary the current. Okay. So what are the various variables? What are the different variables here? You can choose the material. Okay. You can choose the area of plate. You can have a variation in the intensity. Okay. You can keep changing the intensity, because we also know that irrespective of the intensity, something changes, some doesn't change. So one can play with the intensity to understand how the effect of intensity is there on the photoelectric effect. The voltage applied can be varied. Of course, this is the most important thing for us. You can vary the voltage to obtain the stopping potential. What is stopping potential? Where the current becomes zero. Okay. And then you vary the wavelength of the light. So this is the various things you have. Okay. For this demonstration, I choose copper, or I choose sodium. Okay. And then I found that at wavelength of 360, the stopping potential is minus 1.6 volts. Okay. I will just explain you a little later. Okay. So let's go back there. If I fail again, I will not wait. I will just go to the next slide. Okay. Stop here. Okay, so we go here and we go to the photoelectric. Okay, so same thing here, aim theory, all the theory was there. Okay, whatever I just explained, I have taken exactly from this so that you don't see any difference. So there are various graphs connecting the photocurrent, applied reverse potential, frequency at different intensities. All those things which you can vary is available here. Okay. So the procedure is simple. Again, whatever I mentioned you select this, you select the area, you select the light source, measure the reverse current, plot the current versus voltage, and determine the threshold voltage, and repeat the experiments for various intensities and various wavelengths. So what we do is we do the experiment with various wavelengths, okay, to obtain the wave function. Sorry, the work function. This is what I wanted to do this experiment. Yeah? So lucky we have the flash running, so no need to worry about it. Okay, so let me choose the material sodium. Okay, give me a minute, ma'am, sir. Yeah. Come back here. So I chose sodium. I can choose any random area. Let me choose a area of like 0.3, or I can go for a maximum 0.5. Doesn't matter. Okay, I just choose 0.3. I choose the maximum intensity, okay, which is 30 watt per meter square. Okay, and then I switch on the light. When I switch on the light, if you see the default is 100 nanometers, and already without any bias, see bias is 0, I do see a current. Of course, it is understood because 100 nanometers is a very deep, it's a deep ultraviolet region, high frequency, and most of the metals do start showing photoelectric effect at that point. Okay, so what I do is, just to demonstrate, I go and change my current, my voltage, my frequency. Let me go to 540 nanometers. Let me go something about 480 nanometers. Doesn't matter. Okay, that's very difficult to control. Okay, so this is 486 nanometers. Yeah. So at 486 nanometers, I see some current and no output. Okay, so what I do is I change. Okay, I see the current, right? Then I keep changing my voltage. Keep changing the voltage. What is my requirement? I should keep varying my rheostat, keep changing the voltage bias till I get current, which is 0. Correct? That's the stopping potential. Yeah, exact at point minus 0.4, I have 0. So one can say that the stopping potential for sodium for a specific wavelength of 486 nanometers is minus 0.4. Similarly, I can just go a little much more deeper UV and go to 400 nanometers, 402, 400 nanometers, and again do the same thing. Again, now we know that as I increase the frequency, I need to increase the bias voltage. Okay, so again we see that at exactly minus 1, at 0.9 you do have some current. At minus 1 of negative potential, you have the current to be 0. So for 402 nanometers, the stopping potential is minus 1. Okay, the same thing I can keep on changing. Okay, I can keep on doing it. So what I do is I vary my wavelength, and for each wavelength I make a note of what is the stopping potential, and then I plot it. This is what I'm going to do, right? Which what I have done already, right? So let me show you my PPT. Okay. Yeah, this is what I had done. I varied my wavelength from 546 to 200 nanometers, and for each wavelength I have calculated the frequency, and then I used whatever is the stopping potential which is here. Of course, I didn't bother about the current, the sign. Okay, it is negative, so stopping potential is negative. We know that, so I just put it as positive values here. Okay, so this is what I had done. I used origin to do all these things, so it is easier for me to plot. So when I plot the potential versus wavelength, I see the variation to be, as you see here, as per the theory which we learned. It's not the potential versus wavelength which makes sense, because we like to see what is available in the textbook. So it's the frequency versus potential which gives us the actual variation. And you see here, it is a straight line, and this is for the sodium. Okay, I have done the linear fit so that it comes here. Now, there are two things one can do. If you do not have, because we are actually simulating in the lab, I am able to do this, the entire series, okay, where I know the 0 is at 546. Now in the lab, you may not get all these things. So what you do is you just choose a certain wavelength region. Let's say you choose from, instead of 540, you start from 500 to 300. Okay, so from 500 is somewhere here. So you 500 to 300 is here. So you just choose this part. Okay, so these are the values which you would have got in the lab, actual lab. Then when you convert it to the frequency, you will fill up certain points and you do a linear fit. When you do the linear fit, the straight line where it intercepts the 0 or the x-axis is the actual mu naught. Okay, so this is how one can do in the real lab. Okay, so this is the point where I can stress that virtual lab gives you more freedom to actually go and get the answer. Okay, yeah. So I have this. I know now everything. So I just zoomed in for your own understanding. So this is Ke max versus frequency plot. I can use this equation H equal to Ke max plus W, where H naught is W or the work function. Okay. And the mu naught or the threshold frequency is 5.495 into 10 power 18 hertz. And the work function can be calculated, okay, to be 3.64 into 10 power minus 18 joules. Okay. Furthermore, you can write in terms of electron volts, and the work function of sodium as per this experiment is 2.27 electron volts, which is very, very close to what is theoretical value. Of course, there is no secret here. You have certain equations. In fact, when the simulation is done, all we do in the virtual lab is use the graphic user interface, okay, where we use the theory to simulate. So whatever you input, you're going to get the right output. Doing wrong for this experiment is very limited. I will show you an experiment next time, in the next experiment, where the human error can also be introduced. Okay, we'll just do that in the next experiment. But here, I would stop with this calculation of determination of work function of sodium. Okay, so as an assignment, I would like you to go back and try to obtain the other concepts associated with photoelectric. Okay, for example, you can vary the cancer intensity. Okay, and keep the frequency constant. So you'll get, for constant frequency, different intensity, what is the current variation, and what is the graph. Similarly, for constant intensity and different frequency, you can see what is the case. Okay, and then I have listed out few aims, which are about 6 to 7 aims in the first slide of this experiment. So you can also look at it. So the only way we do is we gain, we get better is by practice. Every physics faculty or physics student knows it by heart now. Okay, so we keep trying out to become better. So I would say, please go back and try on your laptops or whatever systems you have this particular photoelectric effect and play with it, and so that you can get various outcomes. One of the things which I found after getting introduced to this is, when I teach photoelectric effect in my own class, I'm able to do a better job, because quickly I can simulate few of the things which I think a student can understand better, and I can go and give it in the class with the figures, so that for a given random numbers which students like to change, no one wants to go as per the textbook. They want to have random numbers, a random frequency or random intensity. You can do all these things and still show that the theory is correct. So this is how you can generate more curiosity in the student. Okay, so I think I'm at the end of this demonstration, right? So the last experiment which I thought I will explain you is emission spectra, right? So we are just, what we are doing is we are slowly increasing the involvement of the concepts. Okay, it is becoming more and more involved. right? So we started with Planck's constant, which is very easy experiment and also very pretty important concept to begin with, the entire concept of the story of modern physics. Then we discussed the concept of photoelectric effect, and then I showed you the experiment. The next comes the emission spectra. Of course, emission spectra has been there even much before the introduction of Planck's constant. However, the concept of emission spectra has become more and more clear. The atomic physics model, all the atomic physics models became much more developed. People could understand the physics of atoms and molecules only because of the introduction of quantum theory. Okay, so this is the experiment which we need to do in this present demonstration, emission spectra. So what we do is the following. The aim is to study the emission spectra of hydrogen, neon, and mercury vapors. So these are the three sources you have to look at it. Keep in mind, one of the earliest sources known to mankind, which is other than sun, are the discharge lamps. Okay, so that's how the curiosity of Newton, Melville, and all the subsequent Theodore Melville and all the subsequent scientists became more and more strong, or they become more and more interested to understand the concept of atoms, because the emission spectra, which was considered earlier to be continuous, was no more continuous, but it is discrete lines. So this is the beginning of the entire story of atomic physics. So this experiment, this idea of emission spectra holds a very strong historical context to the development of the entire field, which we know as the molecular, atomic and molecular spectroscopy. Okay, so stories apart, history apart, the actual experiment requires you to have a knowledge of spectrometer, diffraction grating, a mercury bulb, hydrogen bulb, neon bulb, etc. Okay, let me introduce you the laboratory spectrometer, which we also call as spectroscope. So this has the three main components. You have the telescope, and you have something which is a viewing telescope. Both are telescopes. One is to show towards the source, the other towards the eye. Which use it for observation. Okay. Ideally, one of them is fixed, one is not fixed. Okay, you can have both fixed, both moving. Depends on anything. Then you have the central prism table, or you can also put a diffraction grating here. Okay, so I will not spend too much time under explaining you this, because this is something which I assume all the science faculty knows these things. Okay, so you have the collimator and focus knobs, the various knobs to make sure that the image of the slit is clear. Only thing which I want to stress is the slit width. So this slit width is most important because the resolution of the spectrometer is related to the slit width. The narrower the slit, the better is the resolution. Now, what is the problem of this narrowing the slit? You will lose the, you lose the sensitivity, because less amount of light will come through this. Okay, so always there's a trade-off between sensitivity and the resolution, right? So this is something which one can understand further when we go in detail about all these spectroscopy courses. Yeah. So I request you to, probably I should have shown you the actual thing. Just type laboratory spectrometer and you will see a lot of YouTube videos. And I found this video is very, very nice. It's about 10 minutes of demonstration, but it's well explained demonstration. Yeah. Now, just for those, I wanted to introduce you this idea. Atomic and molecular vibrations correspond to excited energy levels in quantum mechanics. Yeah. So the difference between the emission and absorption is always the difference between two energy levels. The atom is at least partially in excited state. So H is the Planck's constant. Okay. Alternatively, we can use this terminology H lambda, H nu, or H omega. Okay. Furthermore, which is more closer to our interest, is excited atoms emit photons simultaneously. Correct? So the idea here is excited atoms. So it is important that you need to excite. How do you excite the vapors? By giving an electrical bias. So that's how the excitement is done. Okay. So when you excite, you do have the output, which is one we call as phosphorescence or fluorescence. Okay. So this is the point about a little bit introduction to the emission. Okay, so the spectra here, the theory, it can be continuous spectra, continuous band of colors is obtained. You can also have absorption spectra, dark lanes are on a bright background. Emission spectra could be spectral bright lines on dark background. So these are the various things which one can see with this experimental experiment of emission spectra. Okay, in this experiment, what we do is we use a diffraction grating optical spectrometer and study the spectra. So what we do is the simple. Okay, we try to vary the. We will try to change. We will try to use the vapors of each of the mercury, hydrogen, or neon, and study how is the diffraction taking place. And eventually, what our interest would be here is to, the final goal of this experiment would be to get the number of lines per centimeter or number of lines per millimeter, okay, of the diffraction grating. This is the output of the experiment. However, for doing this, one needs to have an understanding of emission spectra. So that's why the title of this experiment is emission spectra. Okay. So these are the adjustments you have. We have a spectrometer. So you first thing is you adjustment of telescope. You do that so that the telescope is adjusted by looking to a distant object until the object crosswise were in focus, sharp focus. So this is just to make sure that your image is well made, focused image you see. Then is adjustment of collimator. The slit is opened slightly and is illuminated using a sodium lamp. Okay, this is what you do in a real life spectrometer. So I'm just telling you the same thing here. Okay, the telescope is brought in line with the collimator. So make sure in this case you just make both of them, linear, so that they're in straight line, and you observe one from the other side. You observe from the eyepiece what is the slit, how is the slit focus. Okay, that's how you adjust the collimator, and then you put the prism table. So once you put the prism table, your idea is that prism should be right at the right height. It is at the right level. Okay, the prism table is leveled using the spirit level or by optical method. Okay, in this experiment, we are simulating the normal incidence position of grating and further calculations. Okay, so you can just check the various experiments available already. I think one of the speakers is covering the diffraction grating experiment, so I will just leave this details to him. Okay. So this is the experimental simulator, what you see. I'm going to show you there. Okay, as I said, you need to do the basic things. Make sure that the telescope is calibrated, etc., and you're going to see the lines or emission of the mercury. Mercury vapor lamp is white light source, and if you look at it, there are sharp colors which are coming out. So if you put a grating, what happens is you need to make sure that this is the light source, right? This is the light source and this is the grating. So what we do is we vary this so that we can start looking. Okay, so light is coming through this direction, right? It is going through this and getting diffracted. So it gets diffracted in this direction or this direction, depending upon which one you see. Okay, and then you can see the orders. You can have one order, second order, third order, and so on. So we will just do in this experiment the first order experiments. The idea here is that you have two vernier calipers, right? Okay, so this is the procedure you have. First thing is you calibrate the telescope, start the button, and then you do start the button, switch on the light. Make sure that the vernier reading is set at 0 and telescope at 90 degrees. All these things by clicking on the sliders. I'll show you the sliders. Place the grating button. Turn the telescope to the left, this side or that side. Coincide the vertical cross lines with the green line on the pattern. Note the readings of the vernier 1 and vernier 2. So there are two verniers you see here and here, and you need to note down the numbers, and that's where the human error starts coming in. Okay. Click on the slider under fine angle to get the readings more precisely. Okay. Difference between the two readings on the same vernier. So idea is that if it is diffracted, it should diffract by the same angle this side or that side. So you do have the 2 theta which is there. Okay. You have the 2 theta there, and the mean value of this difference gives you 2 theta twice the angle of diffraction. From this, the value of theta is obtained for a certain color. We start with the green line, assuming the wavelength of green line, which is 546 nanometers. The number of lines per mm is calculated. Okay, so that you have the final answer. So the point here is you will start with a grading of known lines per, known number of lines per mm. Okay, all we do is we work back and do the experiments as that the number of lines of the grating used can be determined using this experiment. Yeah, and in the meanwhile, you will learn about the various emission spectra that is happening for different colors, different vapors. Okay, so this is the number one, calibrate the telescope. So you have a far off things. I think by looking of it, initially I thought it is eyelashes, but probably they were simulating a coconut leaves, which is on top of a tall coconut tree. Yeah, you can see it. This is a distant object, they have it. Okay, then you turn on the light. When you turn on the light, you have the light here. Okay, there is no grating, so you'll see white light, which is exactly here. This is the cross line. This is a cross wire. So you zoom. So when you move it in the experiment, when you move the cursor, move the mouse around, you can start seeing the cursor, and then there is a certain zoom area on the online portal, which you'll see that will show you how is the alignment with respect to the cross wires. So I have just aligned it in the experiment such that it is perfectly matching with that. Okay, I may not be able to do it so easily now. It takes time, but yeah. Then comes the idea of the 2 1 years. Okay, so this is the first 1 year. Okay, and I tried my best to make sure that the 0 is matched, and this is the second one. Hello. Yeah, this is the second one where it is matching at 1. Okay, so this is the second one which is matching. Yeah, so we start with initial thing, so that by doing this, by making it perfectly 0, what we make it is that it is aligned well, and whatever measurements we make, you have it with respect to the 0, which means you can simply subtract the numbers you get and then we get the actual value of theta. So this is the point I'm saying here. When you introduce the grating, you will see various colors, as you see here. Okay, violet to red, just goes like that, and then you can choose the color green. Okay, I tried my best to make the green, but somewhere it is there, it is not there. So again, there's a human error, right? So there's a small error here. So I can move it this side or this side and place it. So just like how you have diffraction in this direction, you also have diffraction here. So you will see on this side as well as this side. So for this position of the viewing angle, you can take the vernier reading here and here. It is in terms of you have this. If you look at it, it's about 30 vernier scale readings, and each of the smallest division is 0.5 degrees. So 0.5 degrees by, so the vernier is 30 divisions is dividing the 0.5 degrees, and so the least count of this vernier for the circular scale is 1 minute. Okay, so using that one can do the experiment further and then look at the different angles. Okay, so that's what it is. You do this and you move it here and you can get the other. Okay, the step 4 is repeat the same for the other side of the grade. Right, so I think I can go a little further here before I show you. Now in the experiment, in the website, they don't give you what is the wavelengths corresponding to various colors, that you can get it from any online thing. So I just picked up from Google Images, somewhere there it is there. So this is the mercury amp spectral distribution. As you see, this is the green, which matches with 546 nanometers, and you have the yellow and so on, and this is the blue. So I just noted down violet is 0.405, yellow is 579, and so on. So you can use these numbers to get the values. Okay, so what is it that you're going to fill? You're going to fill the observation which looks like this. For each color, what is the vernier 1, vernier 2 for right and left part of the correction of the viewing angle? You go this side and the other side of the telescope. Okay, so you will get the vernier readings from each of the angle. You look at it, then you differentiate, you make the difference between these two, vernier 1 minus vernier 2, vernier 2 minus vernier 2, and so you get these numbers and you take the mean theta. So this will give you the 2 theta value. Okay, the difference will give you 2 theta, and then divide by 2, and the wavelength is here. And then what you do is you use the formula and then get the actual lines per mm. Correct. So I'll just stop it here and show you the experiment. Okay. Yeah. So here the same thing, everything is there. You can have a look at it. I go to the simulator. Yeah. I'm scared of logging in. Every time I log in, it is taking a lot of time. Wow. Yeah. So flash is on, fortunately. Yeah. So here is the experiment, right? So one of the first things we do is to make sure that the telescope is calibrated, right? So we go here. I see the coconut leaves very clear here. Okay. So the way it is done, unless you come to the right place, you cannot start. In fact, when the calibration is at 12, there's only one point where it is the best matched, and that's where you can start the experiment. So calibration is done, you start it. Yeah. So what is the first thing? I chose mercury lamp, white lamp. Okay. The first thing is make sure that you align these two. For that, we need to turn on the light. So switch on the light. Light is on, and it is off the crosshairs. So I just move it here. Okay, when I come here, when I zoom there, that's where I hope you are observing this zoom part. Please have a look at it. I just hover it here. In fact, wherever I hover, the zoom button shows you that. Okay. So when I hover here, I can see how good is the cursor with that. Okay, it is slightly off, but it's very difficult to make it perfect. So I will not bother about it at the moment. Okay. Then comes the reading on the vernier scale. Okay, as I said, this experiment will make you aware of what are the human errors we do it, and that's where it is right away. Is it there at 0 or not? It takes time to actually do it. Okay, you need to keep changing a bit here and there to get the right number which you get it. Okay, so that's what it is. So you have one vernier, so I assume it is almost 0, right? And then you do also have this telescope which you can move like this. Okay, so I can just bring it here very close by, and then I can use this fine angle. Okay. It is off, right? So I need to go to this is again off, right? So I need to go a little bit slow. More or less I'm there. Okay. So now you look at it here. This is little bit better. The 0 is there almost. Now look at here. It is there at 180. Okay. I still say it is little away from the point. That's why you don't see this matching. Okay. So we need to play with it a bit. Look at it. It is a 0. This is at 180 degrees. Yeah, it's there exactly. Yeah. So we can go there now. I introduce my grating. The moment I put the grating, you do have the see the colors. As you move there, you see the colors. So as I said, I start with green. So I try to put it at the green. It is little bit, it takes time, but yeah. I'm just done, ma'am. Just a few minutes. We started late. Okay. Again, I'm not sure about it, so I need to check it here, which is I'm slightly away from it. Then I can use this. I'm going off, right? So I can try to get it here. I'm sorry. And what I'm trying to do is I'm trying to use my uh, okay. Yeah, it would take time, but I don't want to lose any more time. So again, you can do this, right? Please play with it. So one of the ways to do is you click on this button and then use your left and right a little bit so that you can match it. Okay, you can just match it a bit. It takes time, but you eventually get it there. Yeah? So again, now I write this numbers. So this is around 340 and some number which you see there. It's about 340 and 20 almost. Okay. It's about not even 20, it is close to 18 or 19. Similarly here, if you look at it, so that is 1 year 1. And here it is about 160 and some 1 year scale reading. And here it is actually matching close to 9. Okay, so then you have this each 1 year scale is 1 minute, so you can multiply with the minute and so that you can get the actual numbers. Okay, the same thing you can do here. You can bring it here in the other side and you can show. Yeah. Now I'm lucky, as you see, I could get it very good, almost close to this, but the other side. Okay, again I need to play a bit. Now the same thing. Now with respect to this is 1 year 1. Okay, look at this thing. Now this is close to 198, sorry, 199 and some number which is close to 20. 20 is matching almost 20 minutes, 199 and 20 minutes. And this one here is giving me 19 and close to 11 or 12. Okay, just need to check it out. So I do have 1 year 1, 1 year 2 varying. And then what I do is I note these numbers and then keep changing. Okay, so keep the numbers 1 year 1 year 2, make note of it, and then you make it. Then you can change the color to yellow. Let's say you can change to yellow and then use these numbers. Okay, again you calculate this, you use this as 1 year 1, use this as 1 year 2, and go there, the other side. Okay, again make sure that it is right, it is off, but you'll get it eventually if you try it. And then you make a recording of this and you make a recording of this, and then you subtract them. Subtracting this gives you the theta. Okay, so that's how you can get, and then you do the same thing for other colors. So for each color you find theta and then you calculate the n. Okay, so the eventual mean is the actual number of your grading. Right, so here in this experiment you are able to use the concept of emission spectra from various colors and you get it. The same thing you can repeat for hydrogen and neon. Okay, this is neon. Oh, Mr. Radius. Okay, so neon gives you these colors. So you can get the numbers of the neons and then do the same experiment. So you are able to look at the spectra of various sources and get some useful numbers out of it. Okay, so I stop this here and explain and I show you what I got for the case of the mercury case. Okay, so I did for two blue. I got 1 year to be 341.17, 160.33. 1 year one to be 199.33 and 1 year to be 19.33. In fact, I took a lot of time to get these numbers because it is not so trivial to get the exact position on the cross hairs as I showed you earlier. Then I subtracted these two, 1 year one minus 1 year one, 1 year two minus 1 year two to get this 141.84, 141. Okay, so the mean and divide by 2 gives me 70.74, and I know for blue it is 546 nanometers, right? So I can use the equation number of lines per mm in the grating is equal to sin theta by lambda, and it turns out to be 1728 per millimeter. Okay, same thing I repeated for yellow. Okay, I got these numbers 16.42 and the wavelength as per the website is 579, and I studied for this 16.1617. As you see, the error is too high. Okay, and then I will say try the other things and try to reduce the error. Okay, so there is a lot of human error, one can get it. So this is another way of teaching the error analysis. Okay, one can look at it in detail. So as an assignment, I would ask you to complete for other colors. Okay, so because it's very low, less time we cannot do everything, and also this particular experiment takes a lot of time to be very color, very correct. Okay, so I would say to summarize whatever we tried till now, we have done 3 experiments. I have demonstrated 3 experiments under the theme of modern physics. Yeah, and tomorrow I would take up these experiments, 1 in optics, laser beam divergence, and 2 on mechanics, rigidity modulus of suspension wire, and Young's modulus non-uniform pattern. Okay, we are having some trouble in getting the flash of this working. In case I cannot complete by today, I will change something else. But so these are the 3 experiments which I planned for tomorrow. Okay, so I thank you for your attention, and in case there are some queries, I am happy to take it. Otherwise, we can do it later. I think everything is pretty straightforward.
Thank you, sir. Thank you very much for your nice presentation. I think there are some queries in the chat box. I request
Okay.
Dr. Sudhir Bharadwaj to present the queries.
Okay.
Thank you, sir. Thank you very much. We have a few queries. So, participants want to ask whether this graph is plotted manually or by simulator.
Can you just tell me again which graph, sir? For which
In the
experiment?
photoelectric effect experiment.
No. I plotted it manually. I took all the data. So I did the experiment yesterday for you. Okay. I took the data. So for every color, for every wavelength, I had. So this is what you wanted, right? Hold on. I'll show you.
Okay, sir. Okay. Thank you.
Yeah.
Over to you, Padma ma'am.
Okay, sir, is it over? No more queries?
No, I think no more queries.
So you're going to get these numbers.
Okay.
For each wavelength, you will get a potential, and then you plot it. So you can use your Excel to plot as well. Okay, no problem. You can use anything to plot or graph sheet, whatever. So, but then eventually you need to get the numbers and you plot it. So that experiment doesn't give you. However, I know of some other experiments in the same virtual lab which allows you to plot it.
I think there are no more queries.
Okay, I'm just reading it. Hold on.
Okay.
There is somewhere one of the things which I remember seeing is the human error. Sir, one human error is that grating is not at the center of the presentation. So yes, this is what we'll do when you experiment. When you do the experiment, you'll do it. But in this case, I find from virtual labs the error is mainly to look at the things. Okay. The another point is maybe the yellow which is there in the virtual lab need not be the right wavelength which I got on the website. Okay. So one can look at it. If you do all the experiments, then you will know what is the closest number. So there is always standard gratings come with the 1800, 1600, and 1700 1800 millimeters lines per millimeter. So we are somewhere close by that. So we need to check what is the right thing we have used. Okay, yeah. And one more question is, any idea about remote labs, sir? Yes, there is. If you look at the modern physics, there is there is an experiment called solar cell. Okay, so Amrita has this solar cell in their place, so you may be able to access remotely. So for that, you need to send a mail and take their approval. You need to book a slot. Okay, exactly at that point, you can just fire it and get the information. Okay, so because the slots are not available every now and then, I didn't choose that experiment, but you may actually explore that as well. So there is a possibility of using the remote lab in virtual labs itself. Yeah, and is the software open source? I'm not sure about it. Yeah, yeah, I'm not sure about it. I don't think it's open source. I think they put a lot of effort to make it. Can we perform this emission spectra by minimum deviation method? Yes, you can do that. But here the option is only with the grating. So you can, in the real life, you can do whatever you like. Do we need to submit assignment to show? No need. No need. Please do it for yourself. Okay, it's fine. Yeah. Please do it so that you are more clear yourself. Yeah. In case there's something, some minor hitches, I can tell you. I'm sure the next speaker is going to cover more in detail. So you will learn more. Yes, ma'am. I think I covered most of the things. Can we check the doublet nature of alkali spectra using this experiment? Yes and no, but I don't see why you need to do this experiment for that. Doublet will give you two lights anyway. Okay, at least you will get to see that with the spectroscope. Yeah. Thank you. Thank you.